Welcome to the deep dive. Today we're looking into something really fascinating from number theory. Twin primes. They seem simple, but there's this huge mystery around them we want to unpack.
Absolutely. And just to be clear for everyone, a twin prime is, well, it's a prime number that's just 2 away from another prime. So there's a prime gap of exactly 2.
Right, like 17 and 19?
Yeah.
Or maybe 41 and 43?
Exactly those. They're the closest primes can be, really, apart from that very first pair, 2 and 3.
Okay, and that leads to the big puzzle, doesn't it? They pop up quite a bit early on, but then seem to get much, much rarer as numbers get bigger.
That's the core tension.
So the question becomes, do they just stop appearing altogether, or are there actually infinitely many twin primes out there?
And that right there is the famous twin prime conjecture. Still unsolved.
Before we get to the conjecture itself, you mentioned the pair, 2, 3. That one's a bit different.
Yes, it's unique. It's the only pair with a gap of 1. So usually when mathematicians talk about twin primes, they mean pairs starting from 3, 5.
Okay, so 3, 5, then 5, 7, 11, 13. Those are the first few real twins.
That's right. And notice something interesting there, that number 5 is actually part of 2 different twin pairs. It's the only prime that does that.
Huh, that's neat. Does looking at these pairs reveal any kind of, I don't know, structure, a pattern?
A very strong one, actually.
Yeah.
Once you get past that initial 3, 5 pair, every single twin prime pair has to look like this. 6n1, 6n plus 1, for some whole number n.
6n to 1, 6n plus 1. Why that specific form? What's special about 6?
Well, think about any 3 consecutive numbers, say n1, n, and n plus 1. One of them has to be divisible by 3, right?
Okay, yeah. Makes sense.
Now, if n1 and n plus 1 are twin primes and bigger than 3, they can't be divisible by 3.
Right, because they're prime.
Exactly. So the number between them, n, must be the one divisible by 3. And since primes bigger than 2 are always odd, the number between 2 odd primes has to be even.
Ah, so n is divisible by 3, and n is divisible by 2.
Which means it has to be divisible by 6.
Wow, okay. So the number smack in the middle of any twin prime pair, after the first one, is always a multiple of 6. That's elegant.
It is, and it helps narrow down the search quite a bit, but it doesn't prove there are infinitely many.
Which brings us back to the conjecture, still one of the biggest open questions in number theory, and it's related to a broader idea too.
Yes, it's actually just one specific case, the Kekel-2 case of Polignac's conjecture. That suggests there are infinitely many prime pairs for any even gap k. But K2, the twin prime case, has been incredibly tough.
This kind of deep dive into complex challenges is what keeps fields moving forward. And speaking of moving forward, this segment is brought to you by Embersilk.com. If you're looking to get up to speed on AI for your business or your own learning, Embersilk is really the answer for AI education and integration. Check them out at Embersilk.com.
So that difficulty with K2 makes the progress we've seen the last, say, decade or so even more remarkable.
You mean Yiteng Zhang's work?
Exactly. In 2013, Zhang proved something huge. Not that there are infinite twin primes, but that there is some number n, some gap size less than 70 million.
70 million, okay.
Such that there are infinitely many prime pairs with that gap n. He proved bounded gaps exist infinitely often.
So he didn't find the specific answer for 2, but proved that an answer, a finite gap, must repeat forever. That feels like a massive conceptual leap.
It absolutely was. And then others, like James Maynard and Terence Tao, jumped on this using similar methods. They managed to drastically reduce that upper bound for n.
And where does that bound stand now?
It's currently at 246.
Wow, 246, down from 70 million. So we know for sure there are infinitely many prime pairs separated by a gap of 246 or less.
Precisely. It's not 2, but it's incredible progress.
It really is. But it also kind of highlights how special that gap of 2 must be, how potentially rare twin primes really are in the grand scheme of things.
And mathematicians suspected this rarity for a long time. Back in 1915, Viggo Brunn proved something called Brunn's theorem.
What did that show?
He looked at the sum of the reciprocals of all the twin primes. So 13 plus 15 plus 17 plus 111 plus 113 and so on. Adding up those fractions.
Okay.
What he found is that the sum doesn't go to infinity, like the sum of reciprocals of all primes does. It actually converges to a specific finite number, Brenn's constant.
So adding infinitely many things doesn't always lead to infinity if they get small fast enough.
Exactly. It's a mathematical sign that the twin primes are incredibly sparse. They thin out really fast.
But even being sparse, the scale is just mind-boggling. I saw a figure below 10 to the power of 18. There's something like 808 trillion twin prime pairs found already.
That's correct. The numbers are immense. And finding the really big ones takes serious computing power. The current record holder, found in 2016, is enormous.
How big are we talking?
The primes are 209,968,630,345 times 21L1 tonight. Each one has 388,342 decimal digits.
Almost 400,000 digits. Unbelievable.
So if twin primes are these special close pairs, what about the opposite? We can talk about isolated primes.
Isolated prime.
Yeah, an isolated prime is a prime number p where neither p2 nor p plus 2 is also prime. So it doesn't have a twin nearby. Like 23. 21 isn't prime, 25 isn't prime, so 23 is isolated.
Okay, I see. So there are twins, and then there are these loner primes.
You could put it that way.
So maybe here's a final thought to leave you with. Brown's theorem, the one showing the sum converges. It actually implies something quite profound.
Which is?
That almost all prime numbers are isolated. Statistically speaking, the vast majority of primes don't have a twin nearby.
That's right. It flips a perspective.
So the real mystery isn't just, are there infinitely many twins? But maybe also, why are the twins we do find so special? Given that most primes seem to prefer being alone.
A fascinating thought. It shows how much depth there still is to explore, even in seemingly simple patterns within the integers. Hopefully this dive gave you a good sense of where things stand.
Absolutely. Thanks for walking us through that. And a final reminder, check out embersilk.com for your AI education and integration needs. Thanks for joining us on the Deep Dive.